The discovery of gravitational waves was something that was monumental because Einstein had predicted it 100 years ago, and it was only measured in 2015.
We practically turned on the instruments, and we see this clear as day signature of a black hole merger. And I don't think we had any hope that's what the first thing we would see is.
Before LIGO first detected gravitational waves, right, there really wasn't a field of gravitational wave astrophysics. Now people's imaginations about what they could possibly detect started to run wild.
Syracuse University has been involved with gravitational wave for a long time. It goes back all the way to Peter Bergman and Joshua Goldberg, who were faculty here. With Peter Solson, we were one of the first LIGO LSE group as part of the LIGO project.
Syracuse University has made a major commitment to gravitational wave astronomy, and we're seeing the rewards of those last 30 years of investment in the discoveries that LIGO is making today.
We are discovering now about 2 black hole mergers a week, but we would like to see that every day, maybe every hour. So we need expertise on data analysis, on instrument sensitivity, and the Syracuse team has it all.
In 2022, the Center for Gravitational Wave Astronomy and Astrophysics here at Syracuse University was established in response to the need we perceived for developing the next generation of gravitational wave observatories that can see these mergers of black holes and neutron stars right back to the earliest times in the universe.
The National Science Foundation is the government agency that has had the vision to see gravitational wave astronomy through. They supported LIGO, they support Syracuse University, and they're now supporting Cosmic Explorer.
The Cosmic Explorer idea is to build a detector, an instrument that uses maybe the same technologies, maybe even better technologies, but on a facility that's 10 times longer. It has arms that are 40 kilometers long instead of 4 kilometers long. We can see 10 times farther away.
There's a lot of technical work that needs to be done to make that factor of 10 scaling a reality. Mirror coating development, new lasers and optics, new quantum states of light that we'll need to manipulate to make this detector 10 times longer.
We have a 4-kilometer interferometer. We're sending our laser light down, and what we're trying to measure is the changes in the differential arm length. That change is tiny, 10,000th of the diameter of a proton. We have to have a way of being able to make that optical coating quiet. We're working to make coatings that are 30 centimeters in diameter, only about 6 microns thick, and make them perfect crystals, isolating thermal motion at very, very high frequencies out of the gravitational wave band.
It turns out that quantum fluctuations, so shot noise, limits our detector at high frequencies, so above around 100 Hertz. We inject this specially conditioned state of light called squeezed light, and we reduce the noise in phase or amplitude and push it into the other quadrature that we don't care about, and we see that our noise levels improve. To go from LIGO to Cosmic Explorer, we're going to characterize the squeeze state to make sure our squeeze state is coupled to the interferometer perfectly.
Cosmic Explorer's exquisite sensitivity will allow us to see into the cores of neutron stars, measure the nuclear equation of state, and discover a piece of physics that no one has been able to unveil so far.
One of the things I hope to see is there's the potential that black holes could form very early on in the universe just from the direct collapse of matter, possibly before most stars have even formed.
With Cosmic Explorer, we are going to see the effects of dark energy in the cosmos. And perhaps we are going to see dark matter, which is most of the matter in the universe, which we don't know what it is, and we think we can get hints at that.
The technologies that are required to build something like Cosmic Explorer really are always at the cutting edge, things that we weren't able to do before, right? And they're pushed forward by trying to accomplish this really hard task.
I was fortunate enough to work at LIGO Hanford for a number of years, so I understand a little bit about how we were able to achieve the super high powers in the advanced LIGO interferometers that we see today. So actually I was approached by the DOE and they asked me whether or not it would be possible to create something called a photoneutralization cavity. And so hopefully my sort of technology will help enable fusion plasmas to actually occur.
The purpose of the center is to promote gravitational wave research and to educate the next generation of gravitational wave scientists.
One of the wonderful things about LIGO and Cosmic Explorer is the amount of student involvement we had. We had undergraduate students who were authors on the first discovery paper. We have graduate students who are building the technologies for Cosmic Explorer right now.
Lots of people want to be astrophysicists and people want to work on optics, but I think we're on the edge of both of these fields. So we need more people to know about instrumentation for gravitational wave detectors. So come join my lab.
With the initial discovery of gravitational waves, we were really at the point of where Galileo was in the 16th century. We know how to develop this technology to observe aspects of the universe that we had no idea even existed today. So the thing I'm most looking forward to in the future is the stuff I currently have no idea about.